In this video, we'll be solving the Pearson Edexcel IAL May 24 paper of Physics Unit 1. Now in the first question, we are given that an engine is used to remove water from a mine. We are told that the engine transfers energy to the water at a rate of 180 kilowatt and wastes at 60 kilowatt. So we are given the power ratings. Now the energy that is transferred to the water is useful because that's what we are doing. We are removing water, so every bit of energy we transfer to the water is useful. So the useful power is 180 kilowatt and the wasted power is 60 kilowatt. Now we are asked to find the efficiency of the engine. The efficiency is equal to the useful power divided by the total power. If we see here, we still don't have the total power. We can just calculate it. The total power is the sum of the useful and the wasted power. So this is 180 plus 60, which is 240 kilowatt. So the efficiency is the useful power, which is 180 divided by 240, which is the total. So option A is the answer. Now for question 2, we are given a graph of an object with its velocity and time. We have to choose which of the following describes the motion of the object. Now the first option is constant acceleration. Acceleration is the gradient of the velocity time graph. So for it to be constant, the gradient of the velocity time graph needs to be the same throughout. So this would be the case, a straight line. However, if we see here, the gradient over here is more than the gradient over here. So this part has a steeper gradient than this part. So this is not option A. Option B talks about constant displacement. Constant displacement means that the area under the graph does not change. But if we look, we gradually keep increasing the area under the graph. There might be a confusion over here. So if you were given a graph like this and asked if this was a constant displacement or not, the answer would be no, because as the time increases, the area under the graph is increasing. So at time t1, this was the area under the graph, but at time t2, this whole part is the area under the graph. The blue area is greater than the red area. So the only case where we have a constant displacement is if the velocity time graph was just this. Velocity and time, the velocity is 0. But that's not the case here, so this is not the answer either. Now the third option is decreasing acceleration, which means that the gradient of the VT graph is decreasing. And as we looked over here before, the gradient over here is larger than the gradient over here. So this is a smaller gradient, this is a larger gradient. So as we see, the gradient is getting smaller and smaller as we go on. So that would mean that the acceleration is also decreasing. So C is the answer. We can also explore option D. Option D talks about decreasing displacement. So as time goes on, my displacement keeps decreasing. The only way it's possible is if we have negative velocity. So stuff like this. In this case, the area under the graph is increasing. Sorry, the area over the graph is increasing. So this area is increasing. And this area is under the x-axis or the time axis. So if this area is under the time axis, then you have a decreasing displacement. In any other case, so cases where the velocity time graph is in the positive side, in the positive y axis or above the x axis, this, as it goes on, the area under the graph is increasing, so the displacement is increasing. Now for question 3, we are given that an object is moving through a fluid. We are given its size, shape and type of flow, and we need to state which of them will meet Stokes' law. Stokes' law is applicable for small spherical objects in laminar flow. So option A is not small, B is not small. Now C has spherical, small and laminar, so that works. In case of option D, we do not have any shape. We need to have a spherical shape. So option C is the answer. Now we need to find which of these equations give us a vector quantity. Now if I do density multiplied by volume, it's just the mass. We know that density is equal to mass by volume. So mass is equal to density times volume. Mass is a scalar quantity, so option A is not the answer. Option B is force times distance moved. This is just work done. Work done is equal to force into distance. So this is work done. Work done is energy, which is not vector. Energy is scalar. Now for option C, we have mass times velocity. This is momentum. So we have P equals to mv. We know that momentum is a vector quantity. So C is the answer. Option D is power into time. This is also energy. We know that energy is scalar. Now for question 5, we are given a graph over here. We are told that a student stretches a spring of original length P to a length Q. So this is P, this is Q, by increasing force. So the force goes from 0 to R. Now we need to find the stiffness of the spring. We'll go to the Hooke's law equation, which is force is equals to the stiffness constants multiplied by del x, which is the extension. Now if we look carefully, our y-axis is length and our x-axis is force. So we need to reorganize this a little. We need the extension to be on the left side. So we have x on the left, kx equals to f. We can divide both sides by k. We get 1 by k into f. So this is equal to y equals to mx plus c, where c is 0. Now the gradient of this graph is equal to 1 divided by the stiffness constant. The gradient of this graph is y2 minus y1 divided by x2 minus x1, which is q minus p divided by r minus 0. So basically q minus p by r. However, this is not the stiffness, this is 1 over the stiffness. So 1 over the stiffness is equal to q minus p by r. So we have k times q minus p equal to r. Hence k is equal to r divided by q minus p. So option D is the answer. Now in question 6, we have to find the work done stretching the spring from its original length P to Q. Now the work done when stretching a spring is given by this equation. So half F del x. So we have half times the force, which is R, multiplied by the extension, which is Q minus P. So we have half into R into Q minus P. and out of the following, the B is the answer. It's not P into R, it's not Q plus P, and in this case it's not divided by 2, it needs to be divided by 2 for this half over here. So B is the answer. Now moving to question 7, we have to describe the center of gravity of an object. If you look through the options, option A says that it's where the mass of the object is located. That's not the case. Every part of the object has a mass, but it may be considered to act through the point of center of gravity. So if it's a ball, it's not like nothing on the surface has a mass and then you have everything in the center. That's not the case. So option B is wrong as well. It's not located there either. We can only consider it to act from there. Basically, the center of gravity is the average of the weight that acts throughout the object. Every point of the object, every atom of the object has its weight. So if I have a ball, this atom has its weight and it's being attracted to Earth. Every single atom would do that. But if we average all of them out, they might be considered to act through the center. So that's the case that's happening over here. So option D is the answer. In question 8, we have a student that's trying to determine the acceleration of free fall. And then we are told that the student uses a stopwatch to measure the time taken for a ball bearing to fall, and that his calculated value of G is greater than 9.81. Now the formula for acceleration is V minus U by T. So the student is dropping a ball bearing and measuring the time. So we cannot use this. We know the distance, we measure the time, and we know that the initial velocity is 0 and we want to find the acceleration. So we use S equals to ut plus half at square. If we assume u to be 0, then we can cancel it out. So we have S equals to half at square. We need to make A the subject. So we have half at square equals to S. A equals to S divided by T square. This is half over here as well. So 2S divided by T square. Now we are told that the calculated value is greater than 9.81. For the acceleration to be greater, the time has to be smaller. We have already measured the distance. The distance is accurate, we can assume. The error is due to the timing. As you can see in the stopwatch as well, in the options as well, we are talking about the stopwatch. So we are talking about errors in timekeeping. Now we need to find out in what cases the time would be less than what it should be. So now in option A, we are told that the ball bearing is moving downwards when the student starts the stopwatch. If that's the case, we have started our timer after when we should have. So we should have started our timer when the ball was here, but we accidentally started over here. So we measured this time instead of this time. So this is what we should have measured, the black one, and the red one is what we measured. So in this case, the red one will obviously give us a smaller time than what we have assumed should be the right one. So A is the answer. We'll explore the other options as well. In option 2, we are told that the ball bearing is moving upwards when the student starts. So it might be a case where we are throwing the ball like this and we start the timer over here instead of here. If that's the case, this entire blue distance is what we record with our timer, but only the black part is what we should have measured. So we taking this amount of reading extra than what we should have. So the time is greater than what we should have recorded. So the acceleration would have been less. So this is not the answer. Option C is the student starts the stopwatch before the ball bearing is dropped. So obviously if you start the timer before it starts, the time you record will be greater. This is not the answer as well. And option D talks about the student stopping the stopwatch after the ball bearing lands. So the ball bearing lands over here and you wait 1 second and you don't react in time, so you are late to stop the stopwatch. If you do that, the time will be greater than what it should have been. So this is not the answer as well. We want when time we record is smaller than what it should have been. So option A is the answer. In question 9, we have one end of an wire connected to mass and the other to a support. And we have a student measuring corresponding extension for each added mass. We are told that the wire broke when the extension was small and then it was replaced with a second wire made of the same material, and the second wire had a larger extension before breaking. Now the thing over here is the wire breaks at a certain strain. So the strain is equal to del x by x. So it breaks down at a certain strain. So for the first option, we talk about having a greater diameter. So even if you have a greater diameter, your diameter is not affecting the original length or the extension over here. Now if you talk about the Young's modulus, which is fx divided by a times the extension, for a given force the extension will be smaller if the diameter is greater. That's correct. So the Young's modulus is a constant. If the area is smaller, the extension will be larger, and vice versa. If the area is larger, the extension will be smaller for a given force, that is. However, the wires break down at the same strain. So even if it's a greater diameter, if x is the same, it's gonna break at the same extension. At the same extension, the ratio will be the breaking strain. So suppose we have S break equals to del A by x. If I don't change this x, A won't change either. So it's not option A and it's not option C. Changing a diameter won't do anything. Option B is if we had a longer length. So if x was larger, so if x became 2x, for this ratio to be equal to the previous breaking strain, we need to add a 2 over here as well. So we have 2 on top as well. So this is the new extension before it breaks, which is twice as before. So if I increase the original length, the extension before breaking will also increase, and vice versa. If you use a shorter wire, it will break at a smaller extension. Now in question 10, we are given a ship of this mass and this acceleration, and we are told that the force produced by the engine is this value over here. Now we need to find the magnitude of the drag force. So the resultant force Fr is given by mass into acceleration. So we have 1.2 into 10 to the power 7 multiplied by 0.03. Now the force by the engine Fe is equal to 8.0 into 10 to the power 5 Newton. And finally we have the drag force Fd, which we have to find out. Now if I draw the force diagram for the ship, we have a forward force by the engine Fe, a backward force by the drag Fd, and the resultant of these two is Fr, the resultant force. So we have Fr equals to Fe minus Fd. and I want to find FD. So I'll make FD the subject. I get FE minus FR. We move it to the left, and we move FR to the right and FD to the left. So we get this equation over here, which says the drag force is equal to the force provided by the engine minus the resultant force. If we look at our options over here, we have minus, plus, division and multiplication. Minus is the answer. So option A is the answer to this question. Now for question 11, we are given that a train moves up an inclined plane at constant velocity, and it moves a vertical height of 25 Newton, and we need to show that the GP is about 400 megajoules. GPE is given by the formula mgh, mass into gravitational the acceleration of gravity multiplied by the height you move. The mass is 1.7 into 10 to the power 6, g is 9.81, and the height you gain is 25. If you calculate this, you'll get 4.17 into 10 to the power 8 joules, or about 417 megajoules. Now for question B, we are given that the train has an output power of 20 megawatts. It takes a time 35 seconds to move the vertical height. So this will give us the work done by the engine in total. So the work done by the engine over here will be the power multiplied by the time. So we have 20 into 10 to the power 6 watt multiplied by 35, which gives us a power of a work done of 7.00 into 10 to the power 8 joules. Now the useful work done we found out in the last question was 4.17 into 10 to the power 8 joules. So the work done against resistive forces is equal to the total work done, so 7 into 10 to the power 8, minus the work done to move the train up. So the answer is 2.83 into 10 to the power 8 joules. Now in question 12, we are given an iceberg, and it's floating in seawater with most of its volume below the surface of the seawater. We are given this diagram over here. So 6.7 meters of it is under the surface of the water, and we are told that the horizontal cross-sectional area is 3500 meters square. We have to calculate the block of the ice's weight. Since it's floating, since this ice cube is floating, it has its weight and upthrust on it because it's in water. Since it's floating, the weight and the upthrust must be equal to keep it in that height. So weight equals to upthrust. So weight is equal to, we need the formula for upthrust. Upthrust is basically weight of fluid displaced. It can be found more easily by the density of the fluid multiplied by the volume of fluid displaced. In this case, it will be the volume of ice that's underwater. Since we know how much of the ice is underwater, we know the length and we know the area. So this volume over here can be found easily. And we are also given the density of seawater. So we have rho FV times G as well, because we want to find the weight, not the mass. If you don't multiply g, you find the mass, not the weight. Now we have the density, which is 1.03 into 10 cube multiplied by the volume that's underwater, which is length times A. The length is 6.7 meters and the cross-sectional area is 3500 meters square. And then you multiply it with G, 9.81. So this weight turns out to be 2.37 into 10 to the power 8 newtons. Now we are given that an identical block of ice floats in water of a lower density than the seawater in A, and a larger volume of this block is below the surface of the water. So we have the same case over here. The weight must be equal to the upthrust, that is, the weight must be equal to rho F V G. Now in this case, G is a constant. However, now the density is smaller. So we have a smaller density over here. For the weight of the iceberg is also unchanged. So this is a constant as well. So the only way for this to remain the same is by the volume of fluid displaced going up. And the way for the volume of ice to increase, so this is the water surface. And this is the first ice cube. Now we want this volume over here to increase. The only way for it to happen is if more of the ice is under the water. So a case like this. Now the volume under the water is increased. So this is how it happens. So the weight of the iceberg must be equal to the weight of water it displaces. So this is the first point. So at a lower density, a larger volume will be needed. So when the density of the fluid is smaller, a larger volume of water needs to be displaced. And that's the answer. Now moving to question 13. Now in this question, we have car A with a constant velocity of 93 meters per second. And at a particular instance, this car A is 9 meters ahead of car B. And at this instance, car B has a velocity of 93 meters per second and it's accelerating at 14 meters per second square. We need to show that the cars are side by side after 1.1 second. Don't be confused by the diagram. It does not necessarily mean that at the finish line they'll be at the same place. It could be somewhere over here, it could be somewhere over here. So suppose for the diagram I draw a line like this, and this is the point at which both the cars are at the same spot or they're side by side. If I take this distance to be S, the distance that car B will cover will be S plus 9 because it needs to travel this additional 9 meters. So for car A, S equals to Vt. Since it's traveling at a constant velocity, car A has a constant velocity while car B is accelerating. So we just have S equals to 93t. Now for car B, The distance that it covers is s plus 9. So basically we'll use the formula s equals to ut plus half at square. We'll use this because we know the initial velocity of car B, 93. This is initial velocity. We know the acceleration. We have an idea about the distance, that it's 9 meters more than car A, and we need to find out time. We don't have the final velocity, so we'll use this. So we have s plus 9, the distance covered, equals to u, which is 93 t, plus half. The acceleration over here is given 14, half into 14 into t square. Now we can replace this s with this because they are the same s. So we have 93t plus 9 equals to 93t plus 7t square. If we move everything to the right, we get 0 equals to 7t square plus 93t minus 93t minus 9. We get 7t square minus 9 equals to 0. And from here I get t square equals to 9 by 7, and t is root over 9 by 7. We don't take the negative because it's time. And this approximates to 1.13 seconds. Now for part B, we know that this car A is 100 meters from the finish line. We need to find out whether car A reaches the finish line before car B. The easiest solution would be to find this S because we have already done the working for it. If I know that this line where they are together is before the finish line, since car B is accelerating, it will eventually have a higher velocity. So after this point, car B will be faster than car A. So car B will finish first if the finish line is to the right of this red line. However, if the red line is here, it means that car A was ahead when it crossed the finish line, and both the cars came to the same or came side by side after finishing. So I need to find out this S and figure out if it's more than 100 or less than 100. So I can use both equations now since I know the time. So S equals to Vt is easier to use. So the displacement of the point at which car A and B are side by side is V, which is 93, multiplied by, I'll use the actual value, which is root over 9 by 7. This will come out to be 105.5. This is greater than 100 meters. So car A reaches the finish line first. So basically this is the point at which both of them have the same both of them are side by side. The cars are side by side after the finish line. Now on to question 14. We are told that a grain of sand quickly reaches terminal velocity when it falls into water. We need to state why the grain of sand reaches terminal velocity. Now the terminal velocity is a constant velocity, and it's reached when the weight is balanced by the upthrust and the drag. So upthrust plus viscous drag is equal to the weight. So this is the answer. If this happens, the resultant force will be 0 and there will be no acceleration. Now we are given a spherical grain of sand with a weight that's given, and we are also given the amount of water that it displaces. So this is the upthrust. We are given that the terminal velocity is about 0.05 meter per second. we need to find out whether Stokes' law applies over here. So Stokes' law is F equals to 6 pi eta RV. So this is the drag force. Now we are given everything. To find out whether Stokes' law applies over here is to figure out if weight equals to upthrust plus drag holds up. So we'll take any of the variables as unknown over here. So either viscosity or the diameter or the terminal velocity. And we'll find out if the value we calculate actually matches with what we are given over here. So we'll assume, the easiest would be to assume that we don't know the terminal velocity. We calculate the terminal velocity with Stokes' law, and finally we compare it with what they have given. If they are the same, then Stokes' law applies over here. If not, then Stokes' law does not apply. The weight of the object is 4.3 into 10 to the power minus 5 newtons, while the upthrust is 1.5 into 10 to the power minus 5. And then you have the viscous drag. The viscous drag comes out to be 2.8 into 10 to the power minus 5 newtons. Now I can use this over here. So 2.8 into 10 to the power minus 5 equals to 6 pi times the viscosity of water, which is 1.2 into 10 to the power minus 3, times the radius of the grain of sand, so which is 1.5 into 10 to the power minus 3 divided by 2. We are given the diameter, but we need the radius in the equation, times the V terminal. Now I'll make the terminal velocity the subject. I'll get 2.8 into 10 to the power minus 5 divided by 6 pi times 1.2 into 10 to the power minus 3 into 1.5 into 10 to the power minus 3 over 2. If I calculate this, I get 1.65 meter per second as the terminal velocity. This is far off the 0.05 we have over here. So this is not equals to 0.050 meter per second. Hence, Stokes' law does not apply over here. Now we have to explain how the temperature of the water affects the terminal velocity. Now, as the temperature of a liquid, so a temperature of a liquid over here increases, the viscosity of that liquid goes down. You need to remember this. However, in the equation, W equals to U plus D, or U plus 6 pi eta RV, the upthrust and weight basically stay the same, but we have this value of viscosity going down. 6 is a constant, pi is a constant. The radius of the dust particle remains the same, it's a constant. So I'll mark the constants in blue. The things that are changing is the viscosity, which is going down, but for everything else to stay the same, the velocity, the terminal velocity must also increase. So as temperature increases, we talk about how the viscosity decreases. So we talk about how if the temperature of the water increases, the viscosity decreases, whereas the weight and upthrust is unchanged. So if weight and upthrust is unchanged, I need the drag to remain the same as well. So the terminal velocity must increase in this case. The terminal velocity increases to keep viscous drag unchanged. Now moving to question 15 over here, we have a question about momentum. We have two identical balls, A and B, colliding. Initially B is at rest, and after the collision both of the balls move in the same direction. We are given the mass of each ball as 0.165 kg and also the initial velocity of ball A, which is given. We are given the final velocity of ball B as well. So if I draw a diagram over here, this is ball A, this is ball B. The mass of both of them is 0.165 kgs. I'll do the initial velocities at the top, the final at the bottom. So the initial velocity of ball A is 0.739, while for ball B it's 0. And the final velocity is 0.691 for ball B and V for ball A, which is unknown. So momentum before equals to 0.7 I'll do mass into velocity, so 0.165 into 0.739 plus 0.165 multiplied by 0. This is 0.1219 kg meter per second. The momentum after is equal to 0.165 V plus 0.165 multiplied by 0.691. So it's 0.165 V plus 0.1140. Now, according to conservation law of momentum, so according to the law of conservation of momentum, I'll write in short form, it's just law of conservation of momentum. I have momentum before equals to momentum after. So if I do this over here, the momentum before is 0.1219, the momentum after is 0.165 V plus 0.1140. V will be equal to 0.1219 minus 0.1140. We first move it to the left and then divide it with 0.165. We get a value of 0.048 meter per second. Now moving to question B, we are given that before the collision the kinetic energy of ball A is this value and of ball B is 0. We have to determine the decrease in total kinetic energy during the collision. So Ke after is half MAVA square. So the kinetic energy of A plus half MBVB square, the kinetic energy of ball B. So we have half into mass of ball A, which is 0.165, multiplied by the velocity of ball A, which we figured it out in the last question, so 0.048 square, and then you have half into mass of ball B, 165, multiplied by the final velocity of ball B, which was 0.691 square. So if I calculate this comes out to be 0.03958 joules. So the change in Ke or the decrease in Ke is the Ke before, which is 4.5 into 10 to the power minus 2 minus 0.03958, and if you calculate this you'll get a value of 5.42 into 10 to the power minus 3 joules. Now in question C, we are given that during the collision there is a resultant force on ball B from ball A. We have to use Newton's laws of motion to explain why ball A decelerates. So ball A was on the left, ball B was on the right, ball A was moving to the right. So during the collision, this is ball A. Ball A will provide a force on ball B to the right, and there will be an equal and opposite force on ball A according to Newton's third law of motion. So force on ball A by ball B. And according to Newton's second law of motion, if there's a resultant force on ball A, it will cause the ball A to accelerate. Since this force is opposite to the direction of motion of A, so A is moving to the right and the force is to the left. Since the resultant force is opposite to the direction of motion, we call it deceleration. So when ball A hits ball B, ball A provides force to ball B towards the right. So by Newton's third law of motion, I can just write N3. Ball B exerts an equal and opposite force on ball A to the left. Now by Newton's second law of motion, I can just write N2. The resultant force on ball A, which is opposite to its direction of motion, causes ball A to decelerate. So this is the case over here. Now moving to question 16, we have our 6 marker over here. We are given an experiment carried out by a student to determine the Young modulus of copper. We are given a detailed explanation of what he did. So the student clamped one end of a copper wet to the bench. So this end we are talking about. And then they had a wire passed over a pulley. So this pulley over here. And masses were added to the other side. So we're talking about this. A meter rule to measure. And a marker that's fixed to the wire. This marker. The student measured the diameter of the copper wire. And now we have to explain what else he needs to do. So what other measurements that needs to be made using this apparatus to find out the Young modulus of copper. Now Young's modulus is given by stress divided by strain. Stress is force per unit area. Strain is extension over original length. So this expression turns out to be F times X divided by A times the extension. A is the cross-sectional area, force is the force applied, so basically the weight of the masses. So we already have the diameter of the copper wire measured. So using that I can find the cross-sectional area, which is pi r square. Since we don't have the radius right now, we have the diameter, so we just have this. The radius is diameter by 2, so we have pi d by 2 whole square, so it's just pi d square by 4. The other things that I need is the original length of the wire. So the length that I will measure over here will be this length over here. So from the clamp to the marker, since I'm tracking the extension at that point of the wire, so we write about that at first. The original length of the wire is measured x from the clamp to the marker. Now the next thing we measure is the extension. So how much the marker moves at different weights. So instead of extension, the main thing we are measuring is if the marker's at this new position, I'll not measure this. The thing I'll measure is this whole length. This reduces the percentage uncertainty since I'm measuring a longer distance. So this distance is remeasured with loads added to determine the extension. The force is actually the weight of the masses. So the weight of the masses is calculated since they are known masses. I can just use W equals to mg over here. And now I have the diameter, I calculate the area. So the cross-sectional area A is calculated, it's not measured, using the diameter A equals to pi d squared by 4. Now you might be thinking that it's done over here, I just do it for one value. But for A-level physics, in most of the cases, you want to do a graph first. So since I know that the Young's modulus is stress over strain, it's basically the gradient of a stress strain graph. So if I have a graph of stress and I have a graph of strain over here, the gradient of this graph is the Young's modulus. Now using the graph, I can find out the stress and strain that the stress and strain can be calculated at different masses. So suppose I add a low mass and then I keep on increasing the masses, I'll get a graph like this. And then I'll draw the line of best fit, find out the gradient, and this will give us a result that's more reliable. So it will reduce the random error since we are drawing a line of best fit, and systematic error is also avoided since we are gonna have the same error on everything. If you don't know the terms, you don't need it over here. You'll need it for unit 3 and 6. but the main idea is if you average out more points, the reliability of your answer goes up. If you just do one measurement, you might have made a mistake somewhere which could cause a false result. But if you do multiple measurements, even if you did a mistake once, it will even out. So before we can draw our stress strain graph, we need to actually calculate the stress and strain. So then calculate the stress which is W by A. Since the force is the weight, I'll name it W over here. So then calculate the stress and strain, which is del X by X. And plot a graph of stress against strain. The first thing we write over here is the one that goes in the y-axis, the second one is the one that goes on the x-axis. So we repeat this. Repeating with different masses, we do this. Finally, draw a line of best fit and find its gradient, which is the Young's modulus. And we are done with our 6 marker over here. Now for part B, we are given that another student attaches a weight of 5 Newton to a copper wire of 0.56 millimeter. We are given the length and the Young modulus. We need to find out the extension. So Young modulus is equals to Fx A times del X. So force times the original length divided by the cross-sectional area into the extension. We are given the Young modulus, which is 1.1 into 10 to the power 11 Pascal. We are given the force, the weight of the weight attached, which is 5 Newton. We are given the length of the wire, which is 2.5 meter. I still need to calculate the area, but we are given the diameter. So the area is pi d square, which is 0.56. I need to convert this into meter first. So into 10 to the power minus 3 meters squared divided by 4. So this comes out to be, you can keep it in the exact form in your writing as well. That would be more accurate, but for showing it might be too ugly, so I'll just do the approximate value. This comes out to be 2.463 into 10 to the power minus 7. So this is the cross-sectional area, and then we have the extension. So the extension will be 5 into 2.5, which is 12.5 divided by 2.463 into 10 to the power minus 7 multiplied by 1.1 into 10 to the power 11. And if I calculate this, the extension turns out to be 4.61 into 10 to the power minus 4 meters. Now moving to question 17. We have a child playing a game. This question is about projectile motion. We are given that a child throws a stone at a given speed and a given angle. and that the stone leaves the child hands at a height of 1.25 meter above the surface of the water. We need to show that the vertical component of the stone's initial velocity is about 5 meter per second and the horizontal component is 4 meter per second. So if I want the horizontal component, it will be some trigonometry over here. If you remember it, then it's just 6.3 cos 55, but I'll show you how to derive that. So if I draw a line from here, this is a right angle triangle and the hypotenuse is 6.3 meter per second. The horizontal component is this adjacent one, so cos 55 will be the horizontal component, so this horizontal divided by the hypotenuse, which is 6.3. I'll just do horizontal. So the horizontal component will be 6.3 cos 55 degrees, and the vertical component is this bit over here, so this is V. For this I use sine, since this is the opposite of 55 degree. This is the 55 degree angle, so sine 55 degree is equal to V by 6.3. Vertical component is 6.3 sine 55. So I'll just erase the drawings over here. The horizontal component is 6.3 cos 55. The vertical component is 6.3 sine 55. So vertical vertical V is 6.3. This is U because this is the initial velocity, so I'll just do U. Vertical U is 6.3 sine 55, which is 5.16 meter per second. Horizontal initial velocity is 6.3 cos 55, which comes out to be 3.61 meter per second. Now I want to find the greatest height above the surface of the water reached. So when the ball is thrown like this, it moves in this parabolic path, and at this point we have a maximum height. The maximum height is this many meters above the throwing point. The important thing to notice over here is horizontal and vertical motions are independent of each other. So nothing is affecting the horizontal motion other than air resistance, which will assume to be negligible in this case. But if for the greatest height, all we need is the vertical movement of this stone. Now at the point where the height is maximum, the vertical velocity is 0. If it had a positive vertical velocity, it's still moving up. So this is not the maximum height, it will reach the maximum height a bit later. And if it's negative something, it means that it's moving down right now. A few moments ago it must have been above where it's right now. However, if it's 0, it means that it's at the highest point. So now we'll just do equations for free fall. So the initial vertical velocity is 6.3 sine 55. We already did this in the last one. The final vertical velocity is 0. We don't know the time. We want to find the distance. And we know the acceleration, it's just minus g. So we will use v square equals to u square plus 2as. we have the final velocity 0 square plus the initial velocity. We calculate this 5.16 square plus 2 times minus 9.81 times s. S is equal to 5.16 square, 2 into 9.81. This is 1.357 meters. However, you need to realize that you're not done yet. This value over here, this S is 1.357. But if you notice the starting point, it's from the point where the stone is thrown. If you look over here, this is the point at which the stone is thrown. So it will move in this parabolic path, and S is this value over here. However, we also need to account for this extra height, the height at which the stone was thrown from. So max h is equal to 1.357 plus this distance over here, which is 1.25. So finally we get a value of 2.61 meters above the surface of the water. Now in part C, we are given this tire over here. We are given that the tire is 0.8 meters in diameter and it's 3.9 meters from the side of the water. So we have to deduce whether the stone thrown by the child lands inside the tire. So we want the horizontal distance to be in this region over here. In this region, the horizontal distance, so this part is horizontal, will be more than 3.9 meter. So this is 3.9 meter, and I want to find this over here. The ending point is 3.9 plus 0.8, which is 4.7 meters. So I want my SH to be between 4.7 and 3.9. If that's the case, it lands in the tire, otherwise it doesn't. Now for this I am gonna use both vertical motion and horizontal motion. At first we'll work with vertical motion to find the flight time. At the point at the surface of the water, the vertical displacement is minus 1.25. Since we are taking every upward movement as positive, since that's the initial direction of vertical motion, we started moving upwards first, if we are considering vertical motion only. So the displacement over here is minus 1.25, acceleration is minus g, u is the initial vertical velocity, which is 6.3 sine 55 degrees. I want to find the flight time over here. I'm gonna need the flight time because that's what I'm gonna use to find the horizontal displacement. So in this case I use S equals to ut plus half at square minus 1.25 is equal to 5.16 t plus half into minus 9.81 t square. From here I move everything to the left. In that case I get 4.905 t square minus 5.16 t minus 1.25 equals to 0. We solve this for t and we get the values of t to be 1.255 and minus 0.203. Since we are not considering negative, since this is time, we get this value for the flight time. Now I'm considering horizontal motion hm. The horizontal displacement will be the initial horizontal velocity multiplied by time, since we are assuming air resistance is negligible. Initial horizontal velocity is 6.3 cos 55. We have calculated this in part A, and we multiplied 1.255 with this. We get 4.53 meters. And if you check over here, it's less than 4.7 and more than 3.9. So I'll just write this inequality over here. It's 4.7, yeah. Therefore, the ball lands in the tire, or the stone lands in the tire. So this is the case over here. Now moving on to question 18, we have a lorry that's crossing a bridge, with the bridge being supported by two columns. We are given forces P and Q acting on the bridge from the columns. We are given that the center of gravity of the bridge is at its center, so it's a uniform bridge, and at a particular time the lorry is 35 meters from point X, so this distance over here. Now we need to calculate the magnitudes of forces P and Q, and we need to take moments about point X. So if we are taking moments about point X, the force from the lorry is both the force from the lorry and the weight of the bridge is clockwise, whereas the force Q acts anti-clockwise. So this is a question about moments. So the clockwise moment, CWM, clockwise moment is F lorry times 35 plus weight of the bridge multiplied by 35 plus 25, which is 60. So we have force from lorry into 35 plus weight of bridge into 60, whereas the anti-clockwise moment is the length of the bridge, so add a 60 to it, 120 multiplied by Q, so Q into 120. Now for the bridge to be balanced at this point, both of them must be the same. So clockwise moment equals to anti-clockwise moment. We are given the force from the lorry, which is 4.2 into 10 to the power 5 multiplied 35 plus the weight of the bridge, 9.8 into 10 to the power 5 multiplied by 60. This is equals to Q multiplied by 120. Now Q will be equal to 4.2 into 10 to the power 5 into 35 plus 9.8 into 10 to the power 5 into 60 divided by 120, which comes out to be 6.125 into 10 to the power 5. Now we are done with Q, but we still need to find P. For P, we don't need to use moments now. We can just use the fact that since the bridge is stationary, the resultant downward and resultant upward force must be the same. So the upward forces is P and Q. The downward forces are weight of the bridge and force from lorry. So they must be equal. We're going to use this equation now. So if we come over here, we get P plus 6.125 into 10 to the power 5 equals to the weight of the bridge, 9.8 into 10 to the power 5 plus the weight of the lorry, or the force from the lorry, 4.2 into 10 to the power 5. Rearrange this. And then we get the value of P, which is 7.875 into 10 to the power 5 newtons. That's the value of P and Q. Now moving to part B. We have to explain why force Q increases as the lorry moves across the bridge. So this is the scenario over here. This is the bridge. This is P. This is Q. this is the weight of the bridge. These are the ones that remain constant, like the location of them remain the same. However, the force from the lorry goes from here to somewhere over here as it moves. So you have this point X and this point Y. So if you consider about X, the distance between X and the force of the lorry, so the center of gravity of the lorry increases. So the moment about X will also increase. The moment due to the lorry will increase. So the clockwise moment is increasing. The anti-clockwise moment must also increase then. And there is only one force that's giving me an anti-clockwise moment, and it has a fixed distance. So I want my clockwise moment is increasing because the lorry has the same weight, but now the distance is greater. So my anti-clockwise moment must also increase to balance it. Now in case of my anti-clockwise moment, the distance is fixed. This distance over here is fixed. So the only way you get a higher anti-clockwise moment is by having force Q increasing. So that's what happens here. So this is the answer we go for. We talk about how the distance of the center of gravity of the lorry from X increases, and hence the clockwise moment about X increases. However, the sum of moments must still be 0. So basically clockwise moment equals to anti-clockwise moment. And for that to happen, anti-clockwise moment needs to increase. And since this distance over here from X to Y, or from X to the force Q is unchanged, it's the force Q that must increase for this to happen. Now moving to question 19. We are given a person and he's going on a zip line. We have to draw the free body force diagram over here. We talk about how the person is accelerating and there are 3 forces acting on him. We are not told that air resistance is negligible, and since this person is moving, we have to think about air resistance. He is moving in this direction, so the air resistance will be in the opposite direction. We have air resistance here, and we have his weight over here, the downward force, and then this is the contact with the wear. So the wear is giving him a force in this direction. So that's the force from the wear. Force from wear. This isn't necessarily tension. This is a contact force actually, because the person is holding on to the wear. The wear has a tension with the wheel and the cable, but the person does not have a tension. Tension is not acting on the person at this moment. Now we have this question over here. We are told that at a particular instant, the tension in the cable is 1200 Newton and the angle is 144 degrees. And we need to show that the force on the wheel is about 740 newtons. So this tension and this tension is 1200, and we basically want to find this force over here. So we need to find the component of the 1200 Newton acting in this direction over here in the dotted line. The half of 144 degree is 72 degree, and since this is adjacent, we get 1200 cos 72 plus, if we look on this side as well, I'll use a different color for this. So on this side, this angle is 72 degrees as well. This is 1200 as well. So I get 1200 cos 72. So this is basically 2400 cos 72. So this force R I'm labeling it R because it's a normal contact force, is equal to 2 into 1200 cos 72, so 2400 cos 72 degree, which is 741.6 newtons. Now moving to part 2, we are given that there's a force on the wheel from the wear of 800 newton, and the angle between the force from the cable and the 800 newton force is 150 degree. We have to determine the magnitude of the resultant force using a scale vector diagram. So in this case, you need to use your ruler over here. The force from the wear is vertically downward. I'd suggest you draw a 8 centimeter line for this. So 1 centimeter will refer to around 100 newton. Yeah, 1 centimeter is 100 newton. That's our scale. So we have an 8 centimeter line representing 800 newton force from the wear. My diagram won't be exact since I'm not using a ruler. And then we have our force from the cable. If you look at the diagram, the wear is pulling the wheel down, whereas it's the cable that's pulling it up. And there's a net resultant leftward force that causes the person and the wheel to accelerate to the left. And we are given that it's 150 newton. So basically the angle between the force from the wear and this over here is 150 degrees. This angle is 150 degree, but we are drawing a vector diagram, so we'll actually bring it down over here, in fact. So this is how we'll draw a vector diagram. We draw from tail to head, tail to head. So since this angle is 150 degree and this is a straight line, both the red arrows form a straight line. So this angle over here will be 30 degrees, basically 180 minus 150, which is 30 degrees. So you'll put your protractor over here, you put your protractor here, you'll measure 30 degree and then you'll draw a line over here. Now you may ask what magnitude of line you need to draw. Well, here we have it. We have 741.6 newton. Since each 100 newton is 1 cm, this will just be 7.42 centimeters. We draw a line of 7.42 centimeters, which is force from cable. And this is the resultant force, the black line. This is the resultant, and if you do it right, your resultant force will be in the range of 390 to 410 newtons. That's what you'll get if your diagram's right. You need to make sure that this angle over here is 30 degree, and you need to mention your scale as well, for just to stay on the safe side. Now moving to part C, we are told that people take turns moving along the zip line from the high point to the low point, and at the high point they are initially at rest. Now we have to explain why the speeds of people with different masses are always about the same when they reach the low point. If you see in this case, this is a case of converting GPE into KE. So we are converting GPE to KE. We are losing height and gaining speed. The change in GPE is mgh, the change in kinetics energy is mv square. So the amount of GPE that's being lost is equal to the energy of K that's being gained. If you look at the case, this mass and this mass cancels out. So gh is equal to half v square. So the velocity, the final velocity depends on the height, not the mass of the person. It would have mattered if resistive forces were not negligible, but we'll assume the friction between the wheel and the rope to be negligible. So we'll have to talk about our assumption over here. So the first point would be that in this scenario, GPE, or I'll write the full form, so the masses will cancel out. And for safety, you can just calculate what v should be. So if we go from here, we get v square equals to 2gh and v equals to root 2gh. So we can just mention it in our answer with And finally, we talk about the assumption that resistive forces are negligible. And that's it for this paper.